Hello, everybody. So today we are going to start talking about a new chapter, and we're going to be moving into a topic that is known as stereochemistry. So this is a term that is used quite a bit in organic chemistry when you're trying to talk about a specific molecule. Okay. Now, unlike inorganic chemistry, where there's very little variation in chemical formulas, um, there's roughly about 10,000 ionic compounds. But as far as organic molecules and covalent compounds, there are literally millions of those. And that is because of the spatial orientation and arrangement that atoms can have, which are so varied with covalent bonding. Now, you've already seen this as we've already been kind of talking about this in the previous chapters. But this is going to be a chapter that's really going to try to focus and nail down exactly which type of compound it is that we're looking at. And so this can be viewed through a lens of where we're comparing two different compounds and trying to talk about what their relationships are, or if we are just trying to classify a single molecule. So keep that in the back of your mind that when we're trying to talk about a single thing versus a comparison. So let's start off with just that. So the word stereochemistry comes from the word stereos, which is Greek, which means fixed or without change. And so, it's basically we're trying to get a distinct image of a specific type of molecule and really basically narrow it down into a unique category. Okay. So the first place to start in this entire discussion is when we look at comparing compounds. This is again a comparison. We compare compounds. First of all, the very first similarity that we look for is, are they classified as isomers? So what is an isomer? So an isomer are two compounds that have the same molecular formula. They have the same number of atoms in their molecular makeup. Okay. Now, once you've come to this category, well, then there's a branch, okay, between two things here. Okay, now one branch, which we're going to come over here, there's one branch called constitutional, also known as structural isomers. And constitutional isomers and structural isomers are basically compounds that have just completely different connectivity. Meaning that the only thing that they share in common is the chemical formula. Okay, so for instance, if we were looking at this compound here, okay, versus say this compound here. Now, you could classify both of those as alkenes, but as far as their relationship goes, this is pretty much where it stops because they have completely different spatial arrangements. So at this position right here, everybody should see that there is a one hydrogen atom that's associated with that. And at this position right here, there are 0 hydrogen atoms. And so those molecules are put together pretty much completely differently. All right. Now, if, however, if the molecules are put together in the same manner, well, then they fall into the other category, which is what is known as a stereoisomer, which is where we get the theme of this chapter from, meaning they have a shared commonality. And that is, they have the same connectivity. But are different. Now, keep the word different kind of in your mind. Different could mean that they are a completely different molecule, or different could mean that they have different spatial arrangements, meaning technically they're the same molecule, but how one molecule is oriented versus another, we would say they may have different energies associated with them. Look, for instance, like if we're talking about anti versus gauche. And so that kind of lets the cat out of the bag for the classification for at least one of these. So the first classification is what we talked about pretty much all in chapter 4, which is configurational isomers. Okay, so configurational isomers basically just require, configurational isomers require bond breaking to interconvert. And what we talked about in the last chapter is what is known as a conformational isomer. And a conformational isomer basically just require a sigma bond rotation. To interconvert. So the question is that, well, are they the same? Technically, yes. But do they have the same energy? No. Okay, because of how the molecule, how the atoms are arranged. So for instance, if you were looking at this isomer here, and you were comparing it, let's say, to this isomer right here, you know, and you're asked, okay, well, what's the relationship between those? All you would need to do is to rotate around this sigma bond right here to make this molecule. So these have different energy levels associated with them, but, you know, are technically the same compound. So that's what we really focused on in the last chapter with the gauche and the anti and the boat and the chair conformations of cyclohexane. Now, configurational isomers is really where the focus is going to be in this chapter, whereas you actually would have to break a bond in order to get everything to interconvert. And so there are two big camps of compounds that fall into this category. So one camp is when we're comparing compounds that we would say that they are enantiomers. They are enantiomers of one another. And that essentially means that enantiomers are two molecules that are non-superimposable. Two molecules are non-superimposable mirror images of each other. Okay? So, for instance, if you have a compound, let's say, that looks something like this, where you have a methyl group here that is wedged up, and you draw the mirror image of that compound so that, you know, everything is kind of facing in that mirror, like so. The hydrogen atom, okay, that is associated with is here versus here. And you can see that these positions here, you have 4 different groups attached around those atoms there that I've highlighted. And that's a position that is known as a stereocenter. Okay? And a stereocenter is really an atom that is attached to 4 non-equivalent groups. That could be 4 different atoms. That could be 4 different atoms that are not symmetrical to each other. They could be 4 carbon atoms, but if one carbon atom had 2 bonds to another carbon versus 1 bond to another carbon, well, then those would not be symmetrical to each other. Okay? Now, oftentimes it's difficult to see because if I were to turn over this molecule, just, you know, turn it turn it upside down, turn it around and flip it, well, then what would happen to the stereochemistry is you would now see that this position right here would actually now force that methyl group to go up. Because if it's pointing back, okay, and we were to turn it around, well, now it would be pointing in the opposite direction. And so that is a clear indication right there that those two compounds would be enantiomers of each other. They have the same chemical formula, the same connectivity, but are they the same molecule? No, because you'd have to break that bond there with those hydrogens in order for it to interconvert. Okay, so this is one big camp of stereoisomers. Now, the other one that we're going to be talking about quite a bit is going to be what is known as a diastereomer. And the best definition that I have for a diastereomer is it's kind of a catch-all. Once you make it all the way down to this point, if you concluded that the two molecules are not enantiomers of each other, they're configurational isomers, but they're not enantiomers, well then you can say it is a diastereomer by default. So in other words, these are configurational isomers that are not enantiomers. And that's a pretty good working definition for those. So for instance, if we had a compound where, let's say you had this cis compound versus, let's say, this trans compound. Okay, both of those would require bond breaking to interconvert because you can't rotate around a pi bond. But they're not mirror images of each other. So they would fall into this camp kind of by default. All right, so that breakdown kind of goes through everything that you would need to know as far as classifying a molecule based on its stereochemistry. So now we're going to kind of hone in and focus more on how we actually go about classifying compounds that fall down into this category. Now, that right there is a comparison chart, meaning we're comparing two things, okay, when we're making those comparisons. Now I want to kind of dial that back a bit, and I want to talk about when we're just looking at a single compound. So there is a word that is used to describe molecules that can exist and have an enantiomer. And that word is what is known as chirality. Okay? That is anything, okay, and let's specify that, any single item, okay, that can have a non-superimposable mirror image. Okay, and what that means is that there is no internal plane of symmetry. Okay, now let me give you an example of something. So you've been staring at my hand pretty much for most of all of this course so far. Now, even though, you know, you could say it looks like there's a plane of symmetry in the middle, clearly there isn't, okay, because, you know, the thumb is different from the index finger and the little finger, etc. Now, but if you were to take your other hand and you were to kind of superimpose it on top of this one, well, you could see that they kind of match up. So that means that, you know, in nature already has built in it a type of chirality, okay, that's just naturally occurring. Those of you who are going on to biochemistry are going to learn that pretty much all the amino acids that have a chiral center, that particular chirality is of one particular type of configuration. And so that is kind of an interesting thing that kind of nature chose one particular stereoisomer versus another one, okay? And there can be very different chemical ramifications for having one stereoisomer versus another one, okay? Particularly in how those compounds react in the body. So my hands are mirror images of each other, but I cannot put one on top of another and superimpose it. They just don't match. So that's what the word chiral means, okay? And as far as a molecule is concerned, the question you need to ask is, if you're trying to determine is a molecule chiral, you need to ask yourself, can it have an enantiomer? Can it have an enantiomer? Because if it can, well, then it definitely falls into this category of chirality. Okay, so let me give you an example of what I'm talking about. So let's say that you were asked to draw, okay, bromo, chloro, fluoro, methane. Okay, bromo, chloro, fluoro, methane. All right, and so somebody could be like, well, okay, I've got a carbon, I've got a chlorine on one end, I've got a bromine on another end, and this is definitely going to be a tetrahedral, so I'm going to show it as a tetrahedral, so three-dimensional. There's a fluorine, and it's a methane, so that means that, okay, it's got to have 4 groups attached to it. All right, now that compound, the way it sits right now, notice that that carbon has 4 different groups. Those atoms are different. And so that makes that carbon a stereocenter. Now, that doesn't guarantee that this is a chiral molecule, but if you were to go and to draw the mirror image of this compound, meaning if you were to, let's say, have the hydrogen closest to the mirror here, let me just back it up a little bit to be consistent. So, okay, there's the hydrogens, and then we have our spacing, then we have the carbon, then we have the chlorine, then we have the bromine, or excuse me, the fluorine is pointing up like this, and then the bromine is back here, like that. Okay, those 2 compounds, the way that I have drawn them, there is no way that I could twist or orient this molecule in any way so that it would match this molecule, okay? So for instance, if you kind of visualize this, if I were to twist along the plane of where that chlorine is, and let's say I just want to rotate that around so that that chlorine position remains the same, okay? And so now the bromine was in the plane of the page, but now it's going to be pointing back away from us, okay? And the fluorine that was pointing towards us, okay, is now going to be now still going to be pointing towards us, but that hydrogen is now going to be in the plane of where that chlorine is, okay? And I think you can see, okay, that this does not match that, okay, because these atoms are mismatched. So that would mean that these 2 compounds are, in fact, enantiomers of another, and you can say, yes, in fact, that is a chiral compound, okay? Now, to quickly determine this, it is often done, you often just look for stereocenters, okay? So to quickly determine chirality, look for atoms that are bonded to 4 different groups. Okay, what we have been referring to as a stereocenter. And see if there is an internal mirror plane. If the 2 sides are symmetrical, molecule is not chiral. So remember what I said about an internal plane of symmetry that destroys chirality. So you could look at, let's say, this compound here. This is a cis 1,2-dichlorocyclohexane. And you could say, oh, right, well, yeah, we have two stereocenters, in fact, present in this compound right here, okay, where it's attached to 4 different things on each side. But because there is an internal mirror plane that exists in this compound, well, meaning you could fold this molecule right down the middle and it would superimpose, that immediately brings me to the conclusion that this is not chiral. Now the test is to go ahead and to draw out its mirror image, and this is just going to prove this to you, so you don't have to do this every single time. But if you were to draw out the mirror image of this molecule, I think you can see that those are the same. And if you were to just simply to rotate it around so that the chlorines were on the same face as they are over here, you would in fact see that those molecules are the same thing. And so that means that, all right, there isn't an enantiomer of that compound because it's not chiral, because it has an internal mirror plane, okay? So chirality is when you are trying to describe a single molecule. Does it have an enantiomer associated with it, okay? Now, if it does, well, then you have to be able to classify that enantiomer, okay? You have to be able to describe it and say basically what it is, okay? So how do you go about classifying enantiomers? And so there is a set of rules, and I'm getting ready to go through here. These are known as the Kohn-Ingold-Prelog rules, but most people just refer to them as the RS rules. So don't get hung up on the how we describe them. But this is for when we're trying to talk about enantiomers, okay? The first thing that you want to do is to look for a stereocenter. Look for a stereocenter in the molecule. 2, rank the atoms attached to the stereocenter by atomic number. Okay, rank them by atomic number. Okay, 1 being the highest, all the way out to 4 being the lowest atomic number. All right, now, if 2 atoms have the same atomic number, go out to the next set of atoms. Until you find an atom of higher atomic number in comparison. Okay, so I guess that kind of warrants an example. So if you were, trying to determine, let's say you had this system where you had an alcohol here, and you had a group here like this, okay, and you're trying to classify this stereocenter right here and trying to rank everything. Okay, well, obviously you have a carbon, an oxygen, and then an understood hydrogen here. So the oxygen is number 1 and the hydrogen is number 4. So there's no question about that. But then who is number 2 and who's number 3? Now, a common mistake with this is that people will add up all the groups attached to it, meaning the atom that's bonded to more things. Sometimes you think, oh, that's going to be the higher priority one, but that is not the case. what you have to do is actually look at what the atom is bonded to, which in this case is hydrogen, hydrogen, and hydrogen. And this carbon is bonded to hydrogen, hydrogen, and carbon. So it is a comparison between the hydrogen and the carbon that actually makes this distinction, meaning this carbon would be number 2 and this carbon would be number 3 in our ranking, okay? But it is by no means based on the sum of the atoms that it's bonded to, okay? And so a lot of times people will make mistakes about that, and just to kind of give you an example of that error that can happen. Okay, so in this molecule here, if we were to do the same kind of thing, again, it's clear that the oxygen is number 1 and the hydrogen is number 4, and you have a carbon here and a carbon here. Now, if you were making the mistake of adding everything up, you would go, oh, 12, 12, and 12, that's, excuse me, 6, 6, and 6 for atomic number. That means that that's going to be 18, okay? But if you come over here and you go, oh, well, 1, 1, because of the 2 hydrogens here, and then 9 for the fluorine, you'd be, oh, well, 11. So this would have, and that is wrong. Because the comparison is atom by atom, meaning the highest ranking atom here of atomic number is a carbon, and the highest ranking atom here is a fluorine. So the carbon here would be number 2, and the carbon here would be number 3. Okay, so I just wanted to kind of clear that up with you. That was something I did not have straight in my mind until graduate school, and so I want to make for sure that you don't fall down the same pit that I did when this was explained to me. All right, now after you have done that ranking, then what you want to do is number 1 through 4, the atoms. Number the atoms 1 through 4, just like what we did. And if the number 4 group, is pointing away, if the number 4 group is pointing away or is dashed, okay, so it's pointed away from us, then follow the following pattern, okay? So if you go, let's say 1 to 2 to 3, and so you're going like this, that is a clockwise rotation, okay? That is a clockwise rotation, and we associate that with R, okay? Now R stands for rectus, and that means right-handed. So if you were to put your thumb, okay, like away from you and curl your fingers, you would see, okay, that is curling in a clockwise manner when you're doing that, okay? Now, if, however, the orientation is reversed, in other words, you are going 1 to 2 to 3 like this, so that it is counterclockwise, well, then we think of that as what we call an S, okay? An S stands for sinister. So again, sinister is Latin for left, okay? So, sneaky left-handed people, okay? So, and I'm serious, that's the origins, the etymology of the word. So sinister is left-handed. So if you point your left hand and have your thumb away and curl your fingers around, you'll see that you're going in a counterclockwise manner, okay? And if you think this is funny, what you're doing with your thumb and rotating your hands around, just wait till you get to physics 2 and you learn about the right hand rule in there. So this is a common little teaching strategy for kind of remembering which group goes with what, and it is directly tied to how we name these compounds. So that's where the origins of the R and S come from. Now, if you've made it down to this point, you could ask yourself, well, okay, well, what if the number 4 is not not pointed away. Okay, so if the number 4 group is in the front, if the number 4 group is in the front, just give opposite assignment. It's very simple. Okay, so you just have to give it the opposite. So if we were to, let's say, try this out with the compounds that we were looking at just a moment ago, so that chloro, bromo, fluoro, methane compound, so this one, and then I'm going to draw the other one in blue, so the hydrogen, carbon, fluorine, bromine, and chlorine up here. And we were to number it, the number 1 group is obviously going to be bromine, the number 2 group is going to be chlorine, the number 3 group is going to be fluorine, and the number 4 group is hydrogen, and it is dashed pointing away from us. Okay, so we go 1 to 2, 2 to 3, 3 back to 1. That is rotating in a clockwise manner, so I always check that. So R going clockwise, check your number 4 group. Everything is A-OK if it's in the back, and so you would give it an R assignment. So the name of this would be R in parentheses, bromo, chloro, fluoro, methane. Okay. Now come over here to this compound, do the same kind of thing. So we've got our bromine is number 1, chlorine number 2, fluorine number 3, hydrogen number 4. 1 to 2, 2 to 3, 3 back to 1. Hydrogen's pointing in the back. So now you are rotating in counterclockwise manner. You want to think S. Check your number 4 group. Hydrogen's pointing in the back. Everything's A-OK there. So I'm going to give this S assignment. And so the name of this compound would be S parentheses, bromo, chloro, fluoro, methane. Okay. And I know that there are lots of, things where, we're going to do a couple more examples here just to make sure this sinks in, but that's the gist of how it works. Okay. So let's go back to a compound that we saw earlier. Okay. And let's say I want to name this compound here, where if we have a double bond present, and we've got this methyl group here pointing up. All right. Now, in this instance, you look at this and, all right, we've got an understood hydrogen atom here. Great. But I have a carbon, I have a carbon, and I have a carbon. And the problem is that I have a double bond. So what do you do when you have double or triple bonds? So what you want to do is use phantom atoms to turn double and triple bonds into single bonds. Now that means they don't exist. That's why we're calling them phantom atoms, and this is only really for a nomenclature. So if we're coming down here for the assignment then for the system, and we go out here to this carbon, we've got a hydrogen, and then this is bonded to another carbon atom. And then over here, you've got a carbon and it's bonded to 3 hydrogen atoms. Okay. And then you come over here and you've got a carbon, and this carbon is double bonded to a carbon, meaning it's bonded to a carbon once and a carbon twice, and it's bonded to a hydrogen as well. And so that's how we make our distinction. So the first round that we go out, okay, it's pretty obvious that this one has the second lowest priority. So the hydrogen is number 4, and this methyl group is going to be number 3. Now, if you're trying to find your winning biggest atom, you go, okay, well, the biggest atom here is carbon. Well, so is 2. So the thing you go out is to another atom, and then you have a second carbon atom to compare, but now you're comparing it to hydrogen. So that means that this carbon with the double bond would have higher priority, and so would be our number 1 group. and that carbon would be our number 2 group. Okay, so if we want to name that compound, we would go 1 to 2, 2 to 3, 3 back to 1. That's going in a clockwise manner. You check your number 4 group, and it is pointing away from us in the back. So R will be the assignment, and the name of this will be R. And when you number this, you'd want to go number 1, number 2, number 3, number 4, number 5, again for your chain. So this is a pentene. So you have a methyl group at the number 3 position. So this would be parentheses R-3-methyl-1-pentene. Okay. Now, question that's asked is well, okay, well, what if we're in the unfortunate situation where it's not clear whether the number 4 group is in the front or in the back? So what if the number 4 group is in the plane of the page? Meaning you can't tell if it's whether it's in the front or if it's in the back, okay? So a good example of this might be if you had a compound that looked like this and you were given this particular conformation of it. Now, in this case, it's clear where your stereoisomer is, okay? And your bromine is your number 1 and your oxygen is your number 2. This carbon over here is going to be number 3, but your methyl group is in number 4. But you see, it's not pointed forward or reversed, and so you're kind of in a little bit of a predicament. So the way that you handle this is by considering a Newman projection. So since I just taught you how to do that, what we're going to do is we're going to view that molecule down that bond so that we're viewing it so that the number 4 group is in the back, and then we're going to represent what the Newman projection views. Okay, so we're going to draw a circle, okay, and we're not seeing the methyl group now anymore. So, but what's also in the plane is that 2-carbon ethyl group right there. Then coming towards us is the bromine, which I'm going to draw right here. And then the alcohol is going away from us, which I'm going to draw over here. Okay, and now it's pretty clear as to the direction that the groups are oriented. Okay, so this is clearly going R now. And it's definitely going to be R because we've now forced the number 4 group to be in the back by viewing it in that direction. I like this because you don't get access to a model set on an exam. Model sets are useful, but they can be a hindrance if you get used to always having to use them and to not force yourself to learn a method that allows you to view things in a 3-dimensional manner using a 2-dimensional toolkit. Okay, and I think that's where Newman projections really help you in this case. So naming this compound, okay, numbering the longest pair in chain, this is going to be a butanol. So this is a 2-butanol. And so this is going to be R-2-bromo-2-butanol. Okay, so that gets me through pretty much all the stuff I wanted to say about chirality, talking about enantiomers, and going over the RS rules. You are going to do a lot of this in your homework, and so what we're going to do in the next lecture is talk a lot about diastereomers and physical and chemical properties of configurational isomers. And I should probably be able to get through the rest of this chapter in one more lecture. Okay, guys, so as always, if you all have any questions about this, feel free to shoot me an email or post a comment in the comment section, and I'll get back with you as soon as I can. All right, so everybody take care, and I will see you guys in the next video. Bye-bye.